So Rohit Jain is a software engineer at Facebook, and he is currently developing solutions to help low latency queries in Presto at Facebook. RaptorX is an internal project name aiming to boost query latency significantly beyond what vanilla Presto is capable of. Now for this session, Rohit will introduce the hierarchical cache work, including Alluxio data cache. And cache is the key building block for RaptorX. With the support of the cache, we're able to boost query performance by 10 times while continuing the benefit to work with disaggregated storage. Now let's hear from Rohit on RaptorX, building a 10 times faster Presto with hierarchical cache. Take it away, Rohit.
Thank you, Jasmine. Can you hear me?
Yep.
Okay. Let me see my screen. Okay. Just give me a second. Okay, let me know what we can see.
We can see the PDF. Yeah.
Nice. Okay, that's a fantastic start. That's the hardest part always. Okay. My name is Rohit Jain. Thanks for the wonderful introduction. I'm a software engineer at Facebook. Been primarily focusing on the latency sensitive queries at Facebook. And in the over 1.5 years of my career at Presto and Facebook, we have been able to achieve a lot, and we have been able to get more than 20 times faster queries improvement, and doing multiple things. And one of the primary things which we have done is to implement hierarchical caching, and we have been able to achieve 10x 10x improvements for the Facebook scale of petabytes and exabytes of workload. Moving along, so let's talk about Presto a bit. I think Presto is pretty popular open source project. It has a vibrant community behind it. We love and welcome any open source contribution from external communities, and a lot of our crucial features has been committed by the open source community. Presto is a distributed query processing engine. It can process the data from a variety of data sources thanks to its wide range of connectors which it has. Specifically in Facebook, we have got a huge footprint of Presto available. It is responsible for serving most of our analytical workload and interactive workload. All the data scientists, data engineers, analysts, dashboards, various jobs are being served by Presto inside the Facebook. We've got more than 50,000 servers, which is serving Presto. And Presto is responsible for scanning more than 1 exabyte of data every single day. You can read more about Presto in general. There's a lot of information available in the Presto DB pages. We will be talking specifically about hierarchical cache and related challenges in this talk. So this is not a complete picture of Presto architecture, but it does highlight some of these pieces which has been responsible or corresponding to hierarchical cache. Before talking about hierarchical cache, let's talk about disaggregated storage. Disaggregated storage has been a fantastic design pattern which allows storage and compute to scale independently. It is popular in the Snowflake with S3, AWS EMR with S3, BigQuery with cloud storage. What it allows is the compute expert to scale compute independently, the storage experts to scale storage independently. If you're running out of CPU for compute, you just add more nodes to the compute and you can scale. If you're running out of data which grows faster than the compute, you can just add storage nodes and move along. While this is a fantastic architecture, it does impose certain challenges, which is basically you are relying on the remote storage, remote Metastore for every single operations. And while you are solving scaling storage and compute independently, you are making an IO/network as a bottleneck for every single operation, which is a challenge if you want to solve latency sensitive queries. And because each of these multiple calls can introduce additional delays. When you are looking into the architecture, this is like a brief architecture. So what happens, like when you get like the SQL, you have like the planner and optimizer. You connect to Metastore to get partition information. That's like your network call, which is not cheap. Planner sends this partition information to scheduler. Scheduler access the remote storage / warm storage in case of Facebook to get these list of files. This is not a cheap operation. Then scheduler schedule this file with these files, the workload to different workers, and it does so in a way so that the load balancing is taken into the account, basically. And then each of these workers basically opens these files, read footers, and does various things. And then finally, like the results are computed and results are returned back to the worker. Each of these IO calls can be expensive and are calls for huge query latencies for different workloads. Okay, let's see how we have been able to implement hierarchical caching for these sort of things. Caching is not a new solution. It has been known to industries for a very long time, and it has always been the answer for solving remote IO calls. The trick here is to find the appropriate use cases, implement every use case intelligently to make it effective. So let's talk about these one by one. And the important point here to highlight, like all these caching has enabled us to achieve a fantastic query latencies while keeping the disaggregated storage design principles in place. Okay, the first one is Metastore caching. It's a fairly straightforward one. Basically, like for every query, we need to talk to Metastore and ask, okay, what are the list of partitions we need to work with, and we just cache those. So instead of every time we need to ask the partitions information, the partition information could be like your table information, your partition list, various other information which may be associated with the partition. We can ask the cache, okay, do you have this information available? If yes, fantastic. We can avoid the Metastore call if we have that. There's one challenge though. The Hive Metastore is mutable. It can change over the time. So while you are looking for that partition information in your cache, it may not always be correct because the partition behind the scene in the Metastore might have changed. So what we have done is like we have like the versioning caching. Basically, like for every partition, we have a version along with it. And if the partition information along with the version is available in the cache, we make a call to Metastore and see if this version information is up to date or not. So unfortunately, we cannot really avoid all the Metastore call, but it is pretty lightweight compared to the original get partition call, which contains a lot of information and is very heavyweight. This feature has been responsible for more than 20% of latencies decreases. Some of these use cases where we were dealing with a huge number of partitions inside Facebook, because these cases are humongous, we have seen more than 60% of latencies drop with this feature. File list cache, the next one. So the schedule, the Presto coordinator has the partition information. It sends this partition information to scheduler and asks scheduler, hey, can you schedule the work to different workers? And in order to do so, the scheduler, the first thing it does is basically ask the remote storage, what are the list of files you need to work with for these partitions? This feature is actually contributed by the open source community, I think from the Uber and Pinterest. And it is a fantastic feature. The list file often for any heavyweight data storage is not a cheap call. We have seen like every such calls can take more than 100 milliseconds for a system which is overloaded. So this idea is pretty simple, like especially in the high world and the warm storage world, which is the Facebook warehouse storage. The files are immutable, so which they don't change. So this makes it very easy caching. So we just like for every partition, if we see like the list of files, we just cache those in memory and leverage those if the same list of files is asked again. It has allowed us to reduce another remote call whenever this cache trade is possible. Now the scheduler has the list of files to work with. It schedules the workload to different workers. And the Facebook default configuration to scheduling this workload is the load balancing approach. What it means. So before it's scheduling a workload to a worker, it checks which is the worker which is least busy, which is not doing, which has the most resources to process at this point. And when I see resources, I'm mostly talking about CPU. And that has been the case by default, and it has worked great for keeping the load balancing into the account. But when we are talking about latency sensitive queries, this becomes a problem, because if we want to implement multiple such caches, we want to make sure the data and the data related information is localized as well, which means if a file is sent to a different worker for different queries, different workers might end up caching the same information. And if the same file information is sent to a different worker every time, the workers will never get the opportunity to cache and make it effective. So to improve this situation, what we have done is we have implemented affinity scheduling. What does it mean? We basically create the affinity between file, split, and the worker. So if the same file split is seen again, we try to see, hey, let's try to send the split to the same worker. Now, the interesting point is, if the worker is seeing the same split again and again, it has the opportunity to cache various aspects of it and perform better. But the other side is like if the worker which has the affinity to the split, if it is busy doing other things, then we have the concepts of secondary. We are saying, okay, like what is our second best affinity worker available for this particular split? We try to schedule that, and we see like, okay, it may have the opportunity to have that cache available. If even the secondary does not work, we try to take the load balancing approach into the account. We have been trying out more sophisticated scheduling. We are also trying out shadow caching and other ideas with Alluxio, and see how it works. Okay, moving along. Now with affinity scheduling, we are saying, okay, the same file split would be cached, would be basically sent to the same worker again and again. So what is the first operation that happens when the worker sees a file? It basically tries to open it and try to read its footer, right? Footer is basically like the indexes, which tells you where the data buffers might be available in a particular file. The open file and reading the file footer is not a cheap operation. The footer is the hottest block in the file, and it reads again and again. No matter what column you're reading, where you are reading, the footer, the file footer and the stripe footer are the first information you will have to read. And caching those has saved us 40% CPU and latency is decreased. The gains are pretty good, primarily because when you're reading the footer information from the remote storage, you're first reading from the remote, and then you are trying to deserialize that into the object. The caching which we have is already in deserialized format. So not only you're saving the IO cost, but you're saving the deserialized cost. The next one, which we have built along with Alluxio in the partnership, and that has been the source of most impact for these latencies reduction. Depending on the use cases, we have seen 10 to 20 times latencies decrease. I think last year when we started working with Alluxio for this, Alluxio was a service for the caching, and we wanted to avoid all IO costs. We asked basically, can we work together and create a library so that we can remove all these IO costs, which can be responsible for this data caching. And they have been like fantastic partner, and we have been able to come up with this library, which is pretty beneficial for our use cases. The idea here is simple. When we are reading these data blocks from the remote storage, we try to cache those blocks in our SSDs. So each of these workers, we have a SSD available for these data caching and other caching storage. So every time a read request comes, we first check, okay, if we have this data cache available in our SSDs. If yes, we read it from the cache, avoid the IO calls completely. If not, we read from the remote storage and try to cache those. A simple example here is mentioned here. This is basically like a block cache, and our block configuration has been done as 1 MB, which means we are reading, writing, evicting in 1 MB blocks. So for example, if a request comes from 1.1 MB to 5.6 MB, Alluxio is going to issue to remote storage like 1 MB to 6 MB, which means it's going to read like 6 blocks and keep those blocks as cached inside the SSD. So next time if the call comes to read 4.3 to 7 MB, we know that we have already cached like 4 MB to 6 MB. So the additional request will only be made for 6 MB to 7 MB. So slowly and slowly, like if our cache iterates with soft affinity and is effective, we see like less and less data reading from the remote storage and getting like the huge benefits. The next one, the fragment result cache. Here the idea is fairly simple again. The idea is like if a query plan is scheduled on the worker for a certain file split, and we are seeing like if the same query plan is issued again on the same split, why are we wasting CPUs and IOs by reading the data for the same thing, trying to do the operations like aggregated scan and other things for the same files? The better idea would be to just basically for a same plan fragment and the same file splits, if we already have the results cached, we can leverage those. This sounds pretty simple. What are the challenges in this? The challenges is like the queries are never truly same. They always change. Like in the simple example, which is a very simple example of a query, we are saying like the DS is 22 to 24. The next time the query comes, it becomes 26. So basically a slight variation from the query. So what we are saying is like we create different fragments for this query for each DS, right? So basically different plan fragments, and we try to cache these results for 22, 23, and 24, right? If the next time the results, the query request come for 22 to 26, we only need to scan the data and process the aggregations for 25 to 26, hence saving a lot of processing for this case. I'm just doing a quick time check. Okay, good. Yeah, so the idea here is like the partial computed sum for each query plan fragment has been a huge savings on the latencies as well as IO whenever this hit happens. The CPU savings a lot is good because it affects indirectly like the other queries improvement as well, because now you have the more workload to process, more cache rate to go and things like that. Let's look into another example for the fragment result caching. So now we looked into like a static filter. Now let's assume like if our filter is like time is greater than now minus 3 days. This is a very common query patterns inside the Facebook. People are mostly trying to read the latest and fresh data. They're always saying like now minus 3 days. The problem with now is it's always changing. If you run the same query after even a 1 millisecond, it is going to produce a different query plan fragment. How do we solve this challenge? So what we have done is like we have built the partition stats based pruning. What does it mean? So let's look into this example again and try to see if today is the 26th, if we are going to process this information for DS equal to 23, we know that the time greater than now minus 3 days will always be true. So there is technically no need to apply this filter for when we are applying for DS equal to 23. So that's how we prune, we remove these filter conditions and try to make our query plan static to get better cache rate for such combinations. So in this particular case, only for today's date, we are keeping this filter. For rest of the days, we are gonna get rid of this filter and allow us a fragmented result cache to get a better hit. So another interesting thing which we have done along with this, like when the query plan fragment materialize, it always have different variables and things like that into the place. So we try to normalize and canonicalize this plan with deterministic ID generators to make sure like if the same string comes again, we are able to generate a plan which can be used for fragment result caching hit rates. Okay, we did some experiments with PCH against the vanilla Raptor, and we have been able to see more than 10 times better performance, both in terms of CPUs and latencies. This experiment was done with a 114 node cluster with 1 terabyte of SSD available. And this is not the only experiment. As I mentioned, this is not a research project. It is available in the production, and for many of our use cases, we have been able to see similar wins. And this continues to grow, get more attention in the Facebook, and more interactive use cases are leveraging these features now. A lot of information about all these cachings in detail and design is available in PrestoDB blogs. How to use those, each of these caching, which caching makes sense for you can be found in PrestoDB blog, and see how to configure this and leverage those. Thank you. That's all I had.
Okay, thank you very much, Rohit.
Sounds
For the
Any
presentation.
questions?
I have here, oh, hold on one second. I think I have here Beinan from our team who's also been working on Presto, and see if he's got any question for you.
Hey, Rohit, thank you so much for the presentation. It's very informative. Yeah. I just have a question about the Affinity. So what kind of hashing you guys using for this Affinity? I have some concern about what if some worker offline or stop response, will the RaptorX rebuild the entire cache or something?
So this is a fantastic question. Like our Affinity hash algorithms are pretty naive at this point. We just like do the hash of the file path which we are trying to read and try to get the worker along. In the past 6 months, we have seen major challenges with this algorithm, mostly because the workers can keep going down, and if you are doing like this hash of file path module by the worker counts, anytime a single worker goes down, your worker count changes, right? And that disturbs the whole hashing algorithms and things like that. So we have made like numerous improvements while trying to keep the node count stable by basically switching to the jobs, basically the number of jobs. So even if the hardware is down, the job is still alive and trying to connect to the work. That has made our caching a bit more stable. In the past, we have also tried to think about like if the consistent hashing kind of approach would make more sense. But what we have found is like in these environments when the workers are constantly going down and up, the consistent hashing kind of algorithm does not work for us because it will constantly keep shifting the caching from one node to another node. And we have had concerns with those things. So in this approach, when a worker goes down, we wait for the workers to come back and fill in the spot which was vacant. And in that way, like all other machines which are serving, they keep serving whatever cache they were working with. All the cache, like the file list cache, like the data cache or the footer cache or the fragment result cache and everything. Does this answer your question?
Sure. Perfect answer. Yeah, things we can see there's quite a few kind of cache. So Frank Hu from the Slack, he's asking which caching contributes more to the 10 times improvement on the TPC-H benchmark.
It's what we have seen is like the most impactful caching for us has been the data caching, along with fragment result caching in certain cases. If the fragment result caching, the problem with fragment result caching is getting the cache rate high is a challenge. But whenever it hits, it has been like the huge boost. But in the overall, when we are talking about the challenges with the cache hit rate of fragment result caching, the data cache hit rate which we work with Alluxio has been the most beneficial to us.
Gotcha.
But what I would say is like it's not like a relatively straightforward answer, because the Presto architecture is such that the coordinator is a single point of contact for many of things. So the improvement we have made on the coordinator side caching has allowed the more workload and things like that. As I was mentioning earlier, we have found like the coordinate to be bottleneck for us for many things. So it doesn't matter what kind of effectiveness you have on the worker side. If the coordinator is not processing workload efficiently, it won't. So it's kind of a very tricky answer, but if we go by the stats, yes, the data cache has been our most effective cache at this point.
Cool. Thank you for you both. Thank you for Frank for this great question. Here's a question actually from me. You mentioned that you are using some versioning for the Metastore Cache. I'm just wondering, do you need any modification on the Hive Metastore or something similar? Because I'm thinking, how do you maintain this versioning?
How do we maintain the version? Okay, so yeah, so the primary reason for versioning in the Facebook Hive Metastore is basically we have near real-time data availability. So which means as soon as the data is ingested, we allow people to query on that. What it means, like when the partition is still building, right? It is still adding more and more files. We are allowing people to scan those files and access this data. So we have this concept of partitions open and freeze or close. So which means when we say, okay, if your partition is based on the time, which is equal to 1 hour. So in this whole 1 hour, we are constantly adding the files, new files to this partition, right? And when this time partition is closed, we call it frozen. Like now this partition is not mutable, right? But during this time, this is all constantly changing. So we have these versioning concept, like where Metastore is anytime like this partition information change, okay, the new version is available, and it allows us to function during that time while and trying to make sure we are always returning consistent data to the user.
Gotcha. Okay. I'm now more clear now. Okay, I think that should be the last question for this session. It's also from the Slack from the platform. She's asking, Presto RaptorX can be used for the sub-millisecond queries, just something similar to the read-only query on DBMS.
Sorry, are you asking like can RaptorX be used for sub-millisecond queries? Is that the question?
Yes, that's the question.
Yeah, I think like it really depends what the query patterns and how repeatable they are. Many of our use cases are serving sub-milliseconds query performance. So if you're not scanning a lot of data, if the query patterns are very repeatable, we have seen it returns very, very fast in a few milliseconds.
Cool. I think that's the last question. Thank you for your Rohit. Yeah, I think it's a very great presentation.
Thank you. Thanks for having me. Yeah, see you later. Bye.
Yeah, I think that's
cool. Thank you, Vinay. Yeah, and thank you, Rohit, for the great presentation. And then again, if you guys have more questions, you can always fire it away in the community Slack channel, along with the other Alluxio contributors will come help out too. Don't hesitate to post your questions there.